Hello and welcome to the presentation for Digital Systems Lab 7 counters, where we produced 3 separate counters. My name is Cole Panicky. My partner is Cord Kindred. Cord produced the visuals, which you will be observing in the following presentation, and I will be the narrator, and together we produced the rest of the content that you will review here. Here on the up counter, we see that the transition table is fairly straightforward. All we needed to do was increment by 1 binary digit for each state and then shift everything back 1 state. So basically everything here on the current state side is the same on the next state side, shifted back 1. So it becomes very simple to implement. And then that carries over to these 3 K-maps. These 3 K-maps reduce to the following 3 functions, where A represents Q2, B represents Q1, and C represents Q0. Though the transition table was simple enough, the formulas turned out to be somewhat more complex, particularly for N2. N0, of course, is relatively simple. If you gather both the top and bottom inputs into a single loop, it reduces simply to not C. An interesting thing to note is that the formula for N1 can also be represented by B exclusive or C. Here we will see the overall function of the up counter, which was implemented in NAND gates only. Here we've also used the Q0 output to reduce the total number of gates by eliminating the need for inverters. Let's see how it functions. First we enter the state 1, then 2, 3, 4, 5, 6, and 7. And then on the next clock cycle, we'll repeat, and again begin the cycle. The next counter is the ring counter. The transition table for this counter is slightly more tricky than the last. It may seem counterintuitive to start with a state other than 0, 0, 0, but this counter starts out at 0, 0, 1. Where all other states that aren't used are represented by don't cares. Where each of the states does matter, it's simply a matter of bit shifting 1 to the left from the current state. So 1 becomes 2, 2 becomes 4. And of course, 4 then becomes 1 again. We repeat the cycle. The logic simplifies quite well, as each of these represents only a single variable. In fact, it only represents the byte or bit that was directly to its right. It's nearly blissful in its simplicity. The implementation of these formulas requires no gates whatsoever. They're simply a function of one of the other states. So it goes from 1 to 2 to 4 and begins again. Let's watch it in action. First we have to hit the reset button in order to put it into state. Then it begins to cycle through. If the reset button is held, it will maintain the first state. The gray code counter has a slightly more complex transition table. It can trip you up if you don't watch it. Instead of moving sequentially, which it almost does, it bounces around a little bit, so you have to carefully follow from current to next state and from next to the following current state. So here we go from 0 to 1, and then from 1 to 3. So we have to move not to the next current state, but to the third. So 3 then returns to 2, and 2 to 5. So it begins to jump around a little bit, so you just have to pay attention. For this counter, we were asked to implement hazard-free design. Hazard-free design prevents the circuit from ever entering the incorrect state, even for a moment, as gate delays propagate. This is done by including a superfluous loop on each of the K-maps, which produces a superfluous function in the formula. Enters at state 0, moves to 1, then 3. The most important thing is that each state is only 1 bit different from the previous state. That's how a gray code counter works. As you can see, it's counting correctly.